Good afternoon, everyone. We have to go back to discuss the logic series that we have that forms a great part of this channel, and we have to talk today something called the introduction to the rational method. That is another way of saying the foundations of deductive reasoning. And in an age where feeling seems to trump thinking, you hear that these days so much, right? You hear, I feel, I feel, I feel. I rarely hear people today say, I think, let alone I know. In fact, in the culture that we have today, if we can call it a culture, it is actually not well seen to seem to be confident of your ideas. People call you arrogant. They think that just because you have a good vocabulary that you're an elitist, by the way. That I have seen that. Um, and students are sometimes rewarded more, as you all know, for there's even now a percentage in many schools for participation rather than precision. That doesn't happen here at City Tutoring. Here at City Tutoring, we grade you on your knowledge, not on your participation. We couldn't care less. I mean, it's good that you participate, but participation doesn't give us any indication as to your knowledge in that sense. You could participate a lot and say a lot of nonsense, and that's what we have in America today. The loudmouths and people who would have never had airtime 20, 30, 40 years ago, they now have airtime. So this is going to be refreshing for you because I know a lot of you in the audience, you are thirsty, you are yearning for the kind of order, the kind of discipline that we used to have in this country and in the Western world in general. So that's what you're going to get here. I haven't changed. I always say people have changed. I have not changed, and people have changed based on the trends, and I haven't changed only because I've always, ever since I was very uh, sure of my ideas. The only thing that has changed is how to adapt the ideas, but I'm very confident of my beliefs. I am a Christian. I am a Westerner. I am a male. I'm a man. I know that's not popular these days. I am a white person. That's just the way God made me. And I make no apologies. Why should I apologize for the person God made me to be? I am a mathematician. I'm not a perfect person, no one is, but I do know what God made me to be. And you see a lot of people today, they wander around the world, they have no idea where they come from. They go and move around and hop around to different places, but at the end of the day, you are what God made you to be, not what you feel, not what you think you ought to have been, not what you think in your imagination you should be. You are who God made you to be. That is all you are. And we're going to return to the time honored rational method on this channel. So we're going to begin not with TikToks and feelings, but with the first thing we got to talk about is postulates. And I'll show you on the board. But a postulate is also known, it used to be called postulates. Now it's called an axiom. They're both interchangeable in many ways, but we're talking about a proposition that is accepted as true without proof, not out of laziness or relativism, but because of its there are truths that are self-evident in nature, or at least consistent confirmation by experience. Most of you would agree with me, I hope, unless there's something mentally wrong with you, that if you touch fire, you'll burn. You'll feel a burning sensation. It's not pleasant. And so these are the sturdy foundations upon which logical reasoning is built. And postulates are not to be debated in classroom circles with colored markers and group hugs. They are accepted like gravity or common sense used to be. Never a time before, at least as far as I'm aware, some of you, if you're older than me, you might be able to correct me, but I think there has never been a time in Western history when stupidity was as rewarded as much as it is today. There have always been stupid people. There has always been mass thinking, group think. That's why they used to use the term the masses. That's not new. I think what has changed, though, is that people before used to admire thinkers, or at least, if not admire, at least respect them. But we're living in an age where the most ignorant people, the person who you would not even, if you remember your high school years, the people who used to sit all the way in the back of the classroom and were the losers really of the classroom, they actually now are, not only are they very loud today, and they are given airtime, but they're also in Congress. In fact, if you look at politicians today, at least in America, but in many other countries, but it's not my place to name other countries. But in America today, we don't have any politician who is a thinker. Not a single politician, including the president of the United States. Now, I know a lot of people in my audience are not going to like me saying that, because I know a lot of you think that the president is conservative. He is not. He's far from being a conservative. We haven't had a conservative president since, I would say, since Ronald Reagan, actually. To a lesser extent, George Bush Sr., to a lesser extent, and I remember them both. That was the last, I think the 80s really were, and to some extent the early 90s were the last decade of America. We are no longer an America country. We are a postmodern, post everything society. But anyway, I'm going to give you some timeless examples of postulates. I'm going to show you on the board, and then we're going to show you how to make use of this knowledge for mathematical proofs. So hopefully you can see now on the board, these are three postulates, three basic examples. The whole is greater than any of its parts. Number two, through any two distinct points, one and only one straight line can be drawn. Through a point not on a given line, exactly one parallel line can be drawn to that line. This is Euclid's famous postulate, back when geometry was geometry. So these truths are not up for negotiation or emotional reinterpretation. They stand, they are sturdy and unyielding. They are like pillars of reason in a storm of modern pedagogical fuzziness, which is what we have today. The next thing that we have to talk about is, and now we can move to our discussion of theorems. Theorems have hypothesis, thesis, and demonstration. So a theorem is a proposition whose truth is established through a rational argument, a demonstration, if you will. Not to be confused with a TikTok life hack. A proper demonstration is a disciplined, logical progression that draws on other theorems or postulates. So a theorem has to include a hypothesis, which is the assumed conditions or elements, and then you need a thesis or some kind of conclusion, the truth that logically follows from the hypothesis. So what is an example of a theorem? Well, I hope you all know this. If two lines intersect and they form adjacent equal angles, then they are perpendicular. You know that from driving. And so it's important to distinguish between demonstration and verification, by the way. Verification simply verifies if the theorem works in particular cases. But demonstration, however, proves that it works in all applicable cases. It's a crucial distinction, and it's often blurred in today's everybody's right classrooms. So there are particular cases where you can verify the theorem. But we need the supporting tools of the trade. And those are lemma, corollary, and scholium. And I'll show you the definitions of each on the board. And so here we have the vocabulary. We have lemma, corollary, and scholium. or scolion. Scolio, if you're Greek. It's actually it comes from the ancient Greek. So a lemma is a helpful supporting proposition that often precedes a theorem. It's much like an opening act before the headliner, I call it. And then you have the corollary, which is a proposition that follows readily from a theorem. It's sort of like a dessert after a well-reasoned meal. And then, of course, scholium is a critical remark or an important clarification added to illuminate the theorem further. And this is the rational method. It is structured, it is logical, and it's unmoved by fads. It demands precision, and it rewards clarity. And in a world that is increasingly allergic to rigor, it's both a refuge. I find that it's both a refuge and a rebellion these days. And so now we have deductive chain. Well, we can call deductive chains. And mathematics, when it is stripped of gimmicks, glitter glue, and gimmicky acronyms like PEMDAS, and mathematics is at its core a majestic structure of truths that are each logically deduced from others. It's really quite simply a chain of reasoning. And these are called deductive chains, usually. And no, that's not something you wear on some kind of PIM or to customize an app. Each new theorem is not plucked from the air like some, I don't know, some random quote, but it is firmly rooted in earlier postulates or previously demonstrated theorems. And so in this sense, mathematics, I've often said that on this channel, it's really a cathedral of logic, where every new stone relies on those already laid. The vast majority of you are having problems in mathematics because you don't have a foundation. You cannot build a cathedral from the top and then the bottom if you don't have a foundation. And just as if you're a literature person, you can't grasp Shakespeare by starting with the footnotes. You cannot grasp a new theorem without mastering those that came before it. You need grammar to understand. You need vocabulary to understand great literature. How on earth are you going to understand a great literary masterpiece if you don't speak the English language? If we're talking about a literary masterpiece in the English language, you simply cannot. So a deductive chain is precisely that. It's a coherent series of interconnected propositions or logical steps, building knowledge in a deliberate and disciplined manner. It is the very opposite of the fragmented, just Google it. Google it and forget it. That it's a learning style that's so popular today. Young man, you told me, I don't remember your name. There are some young men who told me this, that literally their teachers in the high school level are telling them to just Google it or to use ChatGPT if they need assistance. Those teachers should be fired. If you are a teacher and you are telling your students that they should use Google or ChatGPT instead of you doing your job, you should be fired, effective immediately. And in an ideal world, you should face consequences of some kind. So we're going to talk about direct, converse, and what was the other one? Contrapositive theorems. Because in the world of real mathematics, as opposed to the world of every answer is valid if you can justify for your feelings, there's a delightful precision in the relationships between theorems. So what we're gonna do now is examine the proper taxonomy, and then you have direct theorems, and these are your straightforward workhorses in all this. It's the classic if this, then that. So if a point lies on the bisector of an angle, then it is equidistant from the sides of the angle. We also have the converse theorems, and these are the reverse engineered companions of direct theorems. The roles of hypothesis and conclusion are flipped. So an example would be if a point is equidistant from the sides of an angle, then it lies on the bisector. And then you have contrapositive theorems. We take the direct theorem and negate both the hypothesis and conclusion. If a point does not lie on the bisector of an angle, then it is not equidistant from the sides. And then you have the contrapositive of the converse. And here we flip and negate the converse. An example would be if a point is not equidistant from the sides of an angle, then it does not lie on the bisector. So we have to talk about the relationship among the four types of theorems, because we have to set the record straight. Just because a direct theorem is true doesn't mean its converse or contrapositive will be true by default. Because logic, unlike the trendy educational fads, does not hand out participation trophies. Each theorem must earn its place by proof. You have to prove it. It's not presumption. And so in our earlier examples, we said that where a point on the angle bisector is equidistant from the sides, you saw that not only the direct theorem, but also the converse and contrapositive held true. And it's a rare and elegant alignment. But beware, because not all logic is so cooperative. What if you had I'm going to show you on the board a more deceptive case, where the statement is true, but the converse and contrapositive are not. All right, so here's an example of what I was referring to. If two acute angles have sides that are respectively perpendicular, then the angles are equal. So this statement is true, but the converse and contrapositive are not. And why is that? Because you can easily find two equal angles that are neither acute nor composed of perpendicular sides. So the truth of a theorem, then, is no guarantee of the truth of its logical cousins. Now, of course, all is not chaos. There are elegant connections. If both the direct and the converse of a theorem are true, then brace yourself. Their contrapositives are also necessarily true. It's a beautiful chain reaction. It's the kind of logical interdependence that once defined education before it was replaced with self-paced group coloring activities. But we can spell this out using letters. If we use letters, I'm going to show you on the board a scheme that you can follow. All right, so suppose our theorem, our direct theorem, is if A equals B, then C equals D. So the converse would then be if C equals D, then A equals B. And if both of these statements are true, then the contrapositive must also be true. If A does not equal B, then C does not equal D. And why is that? Because if C were equal to D, then we talk about the assumed truth of the converse, A would be equal to B. So it would contradict our starting assumption. So the entire structure collapses unless the contrapositive holds. If the direct theorem and its contrapositive are true, so are the converse and contrapositive of the converse. So it's really a second part of this. It's elegant. It's often overlooked logical truth. If the direct theorem and its contrapositive are both valid, then the converse and the contrapositive of the converse must also be true. So this isn't feel good guesswork or an optional bonus round. This is rigorous deduction, the kind that used to be required in classrooms before all these standardized tests and multiple choice replaced mathematical reasoning. And we're living in an age where TikTok has now started passing off as a curriculum, and many of you think that it's a curriculum. But let's formalize the logic here. Suppose the following are true. You have a direct theorem. If A equals B, then C equals D, and then you have the contrary theorem. If A does not equal B, then C does not equal D. So if these statements hold water, and they do, then it follows that their mirror reflections also stand firm. Right? And so you have here the converse. If C equals D, then A equals B. And then you have the contrapositive of the converse, which I'll leave that on the board. All right, and then we have the reasoning as to why. The converse must be true. You can suppose for contradiction that C equals D, but A is not equal to B. So that would violate the contrapositive, which stated that if A isn't equal to B, then C isn't equal to D. But here we have C equal to D, an impossibility under that premise, and therefore the converse must be true. Then the contra-reciprocal must be true. So A does not equal B, but if A equals B, then according to the original direct theorem, C must equal D, which is a contradiction. Thus, the contra-reciprocal also holds. And so this is the kind of tightly interwoven logic that would leave no room for fuzzy thinking or vague generalities. An intellectual discipline that is too rarely demanded in today's classrooms, where the word proof, if you ask people to prove things in a classroom today, it's increasingly met with blank stares and smartphone glances. And so now we have to talk about the necessary, what we call necessary and sufficient conditions. We have to arrive at one of the most tragically misunderstood concepts in modern education: necessary and sufficient conditions. It's a phrase that once upon a time was really the foundation of any serious student of mathematics. So to say that the hypothesis of a theorem is both a necessary and sufficient condition for its conclusion means something very specific. The converse of the theorem must also be true. Not maybe, not kinda, not true if you feel like it. It must be demonstrably and logically valid. And I'm going to show you a gold standard example on the board that I had been preparing for you. Both of the statements you're going to see are true. We can say without hesitation or need for a trigger warning that you're going to see that the necessary and sufficient condition for a point to be equidistant from the sides of an angle is that it lies on the bisector of the angle. And we're going to show this by, let me show you on the board. And here you have it. You have direct theorem. If a point lies on the bisector of an angle, it is equidistant from the sides of the angle. And then you have a converse. If a point is equidistant from the sides of an angle, then it lies on the bisector. And I mean, it's very crystal clear. There's no ambiguity here. There's no interpretive learning outcomes. Now, if you contrast what you see here with a direct, let's say we had a direct theorem that said if two acute angles have sides that are respectively perpendicular, then the angles are equal. It sounds nice. And yes, the direct statement happens to be true, but here's the problem here. The converse is false. So just because two angles are equal does not mean their sides are respectively perpendicular. Equal angles can arise in all sorts of ways without resorting to orthogonal acrobatics. And so we have to settle for a far humbler truth. And you can say that having sides that are respectively perpendicular is a sufficient but not necessary condition for two acute angles to be equal. And that is one of the many reasons why we insist on rigorous proofs rather than vibes-based reasoning or even, I don't think they even do reasoning these days. The classics had it right. And maybe if we spent a little less time redefining math as a social construct and a little more time with Euclid, we'd be producing students who know the difference between a theorem and a TikTok trend. But I'm going to show you another application, if we may call it that. All right, so here you have it. If a point lies on the bisector of an angle, then it is equidistant from the sides. So you have the direct theorem, you have the reciprocal theorem, and you have the contrary theorem in here. Now, in reality, it's not necessary to prove the contrary theorem. Neither should you have to prove the contra reciprocal. If you have proven the direct theorem and the reciprocal theorem. Because if a theorem and its reciprocal are true, so is the contrary. On the other hand, if you wanted to prove the contrary and the contra-reciprocal, you could use something called reduction to the absurd, to the absurdum in Latin. I'm not going to do it in this video only because I'm running out of time for other things, but so hopefully this video was helpful. And if it was, please subscribe to the channel because this channel is no nonsense. It's all about the real, classical, rigorous mathematics.